Thank you, Yossi. I'll start us off. Feel free to jump in. I see someone's already mentioned in the chat that they don't have an account. And we can take care of that. It just means that you won't be able to follow along today interactively, but you can, of course, observe. And all of the stuff that I'll be presenting is in our Getting Started GitHub repo, which we need to get linked onto the agenda page somewhere. So let's try and make sure we do that. I'm going to post this in the Zoom chat for now. So everyone should be able to go here and go ahead and clone this as we go. I'll first go over Polaris generically. And then we'll talk about logging in. Actually, no, I guess we'll start with logging in. Let's see. Yep, we'll start with logging in. So to be clear, I've listed what I assume that you guys are coming in knowing and what I want you to learn. So, I mean, I'm assuming that you guys have basic Linux terminal experience, cluster scheduling experience, and of course, you know how to compile code, write code, stuff like that. And generally, I want you to take away that we use module to inspect and modify our shell environments at ALCF. Other facilities use this, so some of you will be familiar with it, some of you may not. So Polaris is our NVIDIA GPU machine. You can see some pictures here. This is with all the doors closed, and we have this nice graphic on the front. Here you can see inside of one of the racks with the different nodes stacked on top of one another. So it's a peak performance of 44 petaflops. Each node has 4 A100s and 1 AMD EPYC CPU, and there are about 560 total nodes. Of those, I think, was it 512 are technically part of the production queue, and then we also have a preemptible queue, which is focused on delivering real-time analysis for our APS experiments. So let's start with logging in. And so I'll bring a shell over. Hopefully most of you know how to log in to a remote machine. But for ALCF, you're just going to SSH with your ALCF username and then typing in Polaris. Let me know if this is too small. I'm sharing on my laptop screen so that things appear larger instead of using my monitor. So you're going to be asked for your password. And of course, you're going to use your mobile pass app or the little push button dongle if you have one of those.
Taylor?
Yes.
You're sitting right now two screens on top of each other. Do you want to put them on side by side?
No. This is fine for the moment.
All right.
Okay. So there you can see we're logged in. We're sitting on Polaris login 04 in my case. There's a couple of different login nodes. And as you log in, you will be placed on one based on how heavily utilized they are. Okay. So let's talk a little bit about the file system. So when you log in, you'll be sitting in your home directory. You can, I think it's just quota, like you can inspect your quota, not -H-S to give you human readable, so you can see how much space you've got. how much you're being, what's your limit, what space is available. And then so you have your home directory. It's fairly small. Let's see, mine might be a little bigger than normal, but I think nowadays the default is 1 terabyte for your home directory, not 100 gigs. And you can also see utilization on your ALCF accounts page, which I provide a link right here. But then we have bigger file systems. If you look at /eagle and /grand, these are two different 200, I think they're 200 or 100 petabyte file systems. And when you look on those, let's see, our project name is training_Polaris. I don't know if we have a project directory defined, but we'll check. Not on Grand. Do we have one on Eagle? No. Okay, let's see. So we may just be using our
yeah, I went with the default, whatever was the default.
I'm just checking. Oh yeah, we do have one there. Okay. So under Grand Projects, Training Polaris, which for some odd reason I have permission to deny. Anyway, for the moment, you only need your home directory. My home directory is probably a bit messier than yours at this stage because I've been using it for a while. So we will start with cloning our repo. So we're going to clone that Getting Started repo into our home directory. I've already done that, so I'll delete it real quick, rerun that command just so you can see, and also so that I know that it's up to date. Okay, we're going to be down in the Polaris directory. Okay, and so when I talk about these file systems, the important thing here is that when you have everyone should have a project that they're associated with on ALCF systems, and it's typically a name that's associated with your project, right? So it should be fairly clear which project is associated with it, which allocation, in case you have more than one. But the point is, your project space is a place where all the members of your project have the same group, and the group is actually the same as the project name. So like if I ever forget what they're called, if I just type in groups on the command line, which I am support staff, so I'm a member of many projects, but you can see like here's a Fusion DL Aurora ESP. Let's see, here's some from some of the Atlas AI work that I worked on. Here's the Training Polaris project, which I'm a part of because of today's boot camp, and you should see this one in your groups. So when you see those group names, they'll be the same as the project names that you have, and you'll either have a space on Eagle or Grand, usually not both. And the point there is that we can give you a lot more working memory on these petabyte file systems as compared to our home, where your home directory lives. So when you need lots of data or big software to be hosted, and you also want to share it with your project members, put them in these spaces. Don't put them in your home directory, because no one can actually see your home directory but you. So if you want to have shareable stuff in your projects, put them in your project space. That's what that, just the point there. Let's see. Somebody asked a question, what's the difference between my quota and quota-s? That's a good question. Not sure. Okay, so next is environment. How do we control our environment? Obviously, you can control your environment however you like. You can start from the ground up, build your software from scratch. But we do try and provide some basic tools, and we use the module, the environment modules program or whatever you want to call it, to manage these things. So we'll go back to my terminal here and start making this big because we're going to start getting a lot of text. So if I just do module list, this is going to show you all the modules that are loaded. I haven't adjusted my environment since I logged in. So these are all the ones that are loaded by default at the beginning when you log in. And you can see there's some Cray modules. Cray, of course, was bought out by HPE, which is the system integrator for our systems, but they're still using the old naming scheme. So all of these Cray modules come from our system installers. You know, things like libfabric. The fabric is the communication layer for all of the internode communication. So that's important. But then, so that module list tells you what's loaded. Module avail tells you what's available on the system. And these are split up by where the modules are coming from in the file system. So if you were to do an ls on this directory, you would see these two modules there. And a lot of these are just text files that you can inspect if you're really curious. But otherwise, it's just trying to list packages that are available that we've installed. And so if you see lots of them down here, things like the CUDA toolkit, we've installed different versions for your use. We have versions of Cocos, we have the HPC toolkit. Let's see, there are various Cray packages, and we can also do something more specific. So if I type in, let's say GCC, to avail, that should list all the available modules that start with GCC. So if you're looking for, you know, some programming or a compiler version on our systems, you can try and find it that way. We also have various Conda environments, which we use for our AI and machine learning frameworks. So if you type module avail Conda, it'll list those for you. And generally for those, what we do is we use the date that they were installed on as a versioning. And the idea is periodically we'll come through and we'll reinstall the whole package from the ground up. And whatever is the latest versions at those times will be there. And so that involves by hand compilation of TensorFlow, PyTorch, Horovod, those packages so that you have whatever the latest versions of those are, and that they're compiled with the you know, CUDA drivers, the MPI drivers, the communication drivers that are needed for the backend. So, and that also ensures that you know, when we want to update things, we just create a new dated module instead of changing everything under the rug for you, which can, of course, lead to confusion and problems. So if we go back here, what else did I? Okay, so we also have module show, and then of course load and unload. So module show will show you what's going on in a module. So let's look at this Conda module. this essentially dumps the text content of the script that is being used to edit your environment. So you can see all the things that we're doing here, and kind of extrapolate what happens, right? So you can see these set env calls, which is clearly telling it where to pull CUDA from. It's adding CUDA to the path. It's adding CUDA to the library path. You can see all the set environment variables that are happening. And then it's executing some things like telling to actually source the Conda environment so that when you load this module, it dumps you into the Conda environment. So I'm going to do bash just to give myself a retreat. But if I do module load, and then, oops, and then this Conda library or module. There we go. So we've got some other modules that were swapped out and loaded. And then I should do Conda activate. Okay. And so when I've got an active Conda environment, if you're familiar with those things, just like virtual env, it prepends a label to your shell there so that you know that you're currently in that environment. So now if I type in which Python, you can see the Python is coming from there. Okay. So right, so I just showed you also how to load a module. So we use module load. You can do module unload to revert that. You can also do module, there's module switch or swap, where you can, if you want to switch versions of a module, you use that one. So if you're going from like GCC 11 to GCC 12, you would do a swap instead of a load, because if you tried to load it, it would say, oh, you already have a GCC loaded. Ideally. So that's module, and that's how we control our environment on ALCF systems. So now if we go to the next step, so next we're going to talk about the scheduler. Polaris was our first machine to use PBS. If you've used ALCF in the past, you know that you may know, otherwise you may not know, that we used to use Cobalt, which was actually an in-house product. But we are moving to PBS. It's open source, publicly available scheduler, and therefore there's extensive documentation outside of ALCF how to use PBS. But we also have a specific document here for some tips and tricks for using PBS on Polaris itself, kind of a getting started notes there. So here again, I'm assuming that that you guys know that schedulers are used for executing tasks on a cluster or a supercomputer. That you've used these either at your university or institute before or on a previous supercomputer. I'm assuming that you know that when you submit a job to a scheduler, you have to define some parameters, right? How long is it going to run? How many nodes do you need? That sort of thing. And then there's queues involved. And then the goals here to teach you how to start an interactive job, submit a job, monitoring a job, and removing a job from the queue. Okay. So I have a little text here about what a scheduler is. But the scheduler is just there so that everybody can submit work, and it is distributed on the system in a fair and efficient way. Obviously we want our system to be almost 100% utilized all the time. So it is going to find the things that will fit in the open spaces, but at the same time, make sure that jobs that need the whole system can get access to that. So you'll notice sometimes our system is fairly empty. And if you check the queue, you'll be able to see whether or not it's draining for a really big job that somebody submitted. Because of course we're a capability facility. We're focused on big compute jobs, doing big science, not single node jobs. So today we'll only be running single node jobs, but hopefully everyone here will eventually be running at more than 20% of the system, which is what we qualify as capability jobs. And that's what we're really interested in facilitating. Okay, so we can run jobs by using the qsub command. Qsub, short for Q, for submitting to the queue. In this example here, we're going to run interactively. So I encourage everybody to open their terminal, log into Polaris. I'm just quickly checking to make sure everyone. I'm just going to quickly dump this here. I had started a live note so that people could see some details, because I know the chat kind of in Zoom dies sometimes. So I posted the Google Doc here. People can cut and paste things if they like. So the instructions that I've included here are sort of generic. You need to know that today we have a specific project name and a specific queue. So I'll go over that. So in this command, we're submitting a job. We want it to be interactive, so that's what the -i is. Otherwise, you would not include the -i. And then -l allows you to submit various custom attributes to that will define what your job is doing. The select, I won't go into the details of, there's a lot of details behind why select is the thing that we're using, but select here just means how many nodes do you want? So in our case, we always want one node today because the queue actually is set up to limit everyone to one node, just so everybody gets a chance to use the system. And then we have another -l, which gives us the wall time. So we need to tell the scheduler how long do we want this node. And we are going to say 30 minutes. So it's hours, minutes, seconds. I don't know why they put the seconds in there, but anyway. So we're going to say 30 minutes. And then we need to define the queue. And today we're going to be using this to fit. There we go. And everybody please unhighlight when they're done highlighting. But today we're going to be using this queue R549009. It's the name of our reservation. So instead of debug, so we do have a debug queue on Polaris, which allows you to submit 1 or 2 node jobs for testing, but you're limited to 1 hour runtimes. So today we'll be using this queue. And then we'll also be using, you have to always include this -a parameter, which defines the project against which you want to charge your hours, because you have a limited number of hours on the machine that you were allocated, and we need to know who we're charging when we run your job. And so today, use training_Polaris. Don't use your project. These are free hours for this morning. I think this reservation runs until an hour or until 1 o'clock. So, use those for this training session. And then last, we also want to tell it which file systems to mount in our job. Okay. If you are not a part of training Polaris, it's 1 node jobs. They shouldn't cost that much. So feel free to use your project name. So just do groups on the command line. Your project name should be listed there. Use your project name if you need to, just to quickly go through this tutorial. Okay, so you need to specify your file systems. In this case, we're only going to be using the home directory, but whenever you're running applications from your project space, you're going to want to mount the Eagle or the Grand file system. So you're going to include that. Usually you're going to want your home as well. So if you put a colon here, you can add Eagle or Grand.
Either can you either do it side by side or bring your screen a little higher, because they can't.
You can't see the bottom of the shell because that's actually not my shell.
Yeah, it was from the
So that's not. I'm not intending for you to look at that right now. When I want to show you the shell, I'll bring it up right here. Is that clear? So right now I'm just using the documentation that's in the GitHub to try and give you guys an idea. Okay, so let's get an interactive job. I think the ideal situation here is that you guys have all swamped the queue and that I can't actually get on here anymore. Queue name was, go back to the Google Doc, that right there. And then I want file systems, go home, assuming I don't misspell that. Okay. I think I've got everything there. We'll see. Okay. So when you submit, you'll see, waiting for the job. If there's a queue, like if you submit to the debug queue, sometimes we only have, we have 8 dedicated nodes for the debug queue. That means we reserve 8 nodes on Polaris for the debug queue. That can grow. Like in principle, there can be more debug jobs if the nodes are free. But let's say the system's busy, everybody's using the debug queue, and you submit an interactive job. You might sit here for a little while until your job makes it through the queue. Okay, so once your job is ready, it dumps you onto the worker node that you've been allocated. So now I'm on an actual worker node. I'm no longer on the login node. And I can do things like inspect the NVIDIA hardware. So, I mean, if I do a module list, you can see those default modules are loaded. That includes this programming environment for NVIDIA HPC. And that means that things like NVIDIA SMI are already in my path. I can see my 4 A100s listed there. So, you can do things like inspect the CPU, right? So you can see your EPYC processor there. And so in principle, in an interactive job, I can do things like compile my code. I can run my application. I will often use an interactive node if I'm debugging runtime errors. You could profile your code, these sorts of things where you really want that quick turnaround, feedback from your software. So that's, I wouldn't run production jobs in interactive shells because it just wastes your time and it leads to other wasted time. For instance, in principle, you could submit a full machine production interactive job, and your shell will sit there and wait for that job to get through the queue. But if for whatever reason your network goes down, you lose your connection, if you lose that shell, that interactive job is dead out of the queue. So you've sat through the queue for no reason. So, I really would limit interactive queues to a single node, maybe 2 nodes on the debug queue for a short period of time. Okay. Going back to the text here. Okay, so I'm going to exit out of here. So that's interactive jobs. And then we also have some examples in the Polaris subdirectory of some submissions. So if you look at the 00 hello world, this is now a submission script that you can pass to QSub. So you would type in QSub and then the submit script. Okay. And what it does here is it, at the top, you can include all of those PBS commands in your submit script. So now you don't have to type them out on the command line. And so I've put my wall time here. You're going to need to edit this. So I'm going to open this up in VI. And I need to replace that with our queue name. So I'll do that. Okay, and then the project is training Polaris. Okay. The other thing you'll see that I've added here is a place for the log files to go. So these are directories where the standard out and the standard error will go. Otherwise, what will happen is PBS will automatically place your logs in a file that's the name of your command with a dot and then an O or an E for standard out or standard error with the job ID following. So in this case, I just told it to bury those in this logs directory so that we don't, junk up the working directory here that I'm working with you guys. Next, you'll see, oh, this is, let me see if I'm maybe jumping ahead of myself by ignoring anything here. Nope. Okay, good. Okay, so here you can see I'm loading a module with GCC inside. I'm telling it how many GPUs there are per node, and then I'm going to launch an NPI exec with the -n tells it the total number of MPI ranks, and then -ppn is processes per node. So the number of MPI ranks per node. Since we're only using one node here, those are the same. Now, what we'll see is those will differ for multi-node, obviously. And here I'm just echoing hello world to the screen. So we should see this 4 times if we run this. And so what I'm going to do is run qsub examples. And this script is really intended to be run or submitted from the Polaris directory, because the logs directory where your output is going to land is also there. Okay, so just be aware of that. So if I do qsub, I should see this output, which essentially gives me the job ID number for this job. Okay. Okay. Now I can inquire with the scheduler about jobs, and I'm going to include my oh, the job's already done. But if you do qstat, you're going to see everybody's jobs on the queue, and you can see there's a lot of stuff going on. You can see the queue, usernames, job names, the job ID. You can filter by various things. So I think -q lets me filter by queue. So if I look at Oh, no, that's not the queue name. That's the project name. Here's the queue name. Oh, I guess that's not right. What is Q? Is it dash Q? Big Q? That work? Oh, well, that tells me a summary of the queue, I guess. So that's, what's little q doing? Huh, okay. Anyway, okay, so my job finished. And I'm going to see, I should see the logs down here. Okay, so it's down here in the logs directory, and it's just the name of my job ID with a dash error or a dot error or dot O. You know, this is standard out, so I should see those 4 hello worlds listed to screen, which I do. Okay. And like I said, you can monitor your job with qstat-u. My job was, you know, this hello world job executes so quickly. And since we have a reservation, we get through the queue very quickly. So once your job finishes, you don't see your job anymore when you do qstat. But I think you can add, is it -H or -A? To get a historical view. I can do man qstat. Let's see. Displaying information for finished or moved jobs with -big H. Conflicting options. I think I have to, do I start with that? Here. Where is it? No examples of that. Okay, anyway, we can look into that later. Okay, so we did submitting the job, talked about getting the status of your job. You can also delete a job with QDel. This hello world job is going to go through so quickly that I'm just not going to be able to show you how to delete that job before it actually runs and finishes. So, and then, like I said, the standard error, standard out is going to land in that logs directory with these prefixes. And like I said, if you don't specify these -O and -Es, it's just going to be the executable name with the, you know, .E or .O plus the job ID at the end in the same directory where you called qstat or qsub. Let's see. Oh, here we go. J-X is history. So let's check that. There we go. So now I can see those finished jobs. So I've included a kind of a PBS cheat sheet down here at the bottom to help you, you know, just do some quick shortcuts. Things that are helpful are, you know, PBS nodes tells you things about all the nodes on the system, so you can understand how many are free at the moment if you're curious. There are things like queue move, which lets you move jobs between queues, or queue alter, which can let you change job sizes and shapes. PBS RStat is useful for understanding reservations. So for instance, if I do PBS RStat now, you'll see our reservation listed here. So we have a reservation from 2 until 1. And you can see the name of the queue that's there. And then we have some queue sub commands as well, some of the details of these things. Useful environment variables in your job. So when you're, you can use these during the job. I often use PBS job ID, for instance, to, keep log files separated and stuff like that. Okay, so let's move on to compilers. How do we compile our code? So again, I'm assuming that you know how to compile and run your code. You have basic familiarity with CUDA and MPI, and we're going to go through the wrappers that Crape gives us for compilers, and how to compile with C++, CUDA, and MPI, and then submit those, because there's some differences. So Cray HP provides these wrappers for the compilers, which just ensure that when you're compiling, you include all the system level libraries that you need to make MPI work. Right? Our systems have custom networks installed, and you need to be able to use the right drivers to gain access to those networks and make your software work. So we have this example MPI, or just a simple example C++ code. So how am I going to run that? And so if you look at the examples, 01.cpp, you can see this is just a straightforward C++ hello world. How am I going to build that? I am going to run, it's a C++, so I'm going to do capital CC for the G++ wrapper. And you can inspect these on the command line. So you can do things like ccc version. And it will tell you information about how this is set up. So this is using NVC++. If you did, for instance, module swap, and you change your programming environment from NVHPC to programming environment GNU, GNU will give you a flat GCC style environment. So you would have to handle all the NVIDIA stuff yourself, right? You would need to load CUDA module. You would need to keep track of that stuff yourself. So we're just going to do, we're just going to copy and paste this here. So it's going to compile this source code and output an executable. I'll just go into the examples real quick. Do that. Okay. So now you see we have this executable here. If I look at, where is it? I don't have an example. Oh, right. Because this is a C++ program. You can just run it on the login node, right? So there it is. Okay, that works. Nothing special there. It doesn't have any MPI, any CUDA. Obviously, we've never run a program like this on Polaris because 95% of your compute power would be left empty. And so now let's move on to including CUDA. So I have an example here that does a matrix multiply on the GPU and a matrix multiply on the CPU, and runs those two and then prints their timing. So you get a GPU timeout you get a CPU timeout. This again does not have any MPI, so it's not parallel across the nodes. It's really just showing CUDA compilation. But nothing changes here because CC already has all the CUDA stuff included. So I don't even have to do anything differently here. You'll notice I'm using the .cu file, not the where to go? Not the .cpp file. And so we can compile that. And you can see that there. And I've included a shell script that submits this to the queue and runs this. I can see that I accidentally did this, which you probably don't want to do. I'm just going to do that, get rid of that. And then we need our project name updated. Training Polaris, and then the queue. Is here. If anyone has trouble following along, let me know. So then I'm going to do Q sub examples 01 under cu dot sh. Hopefully. There we go. So you can see it's already running. Q is nice and open. Okay. And then I should see in my log files, I can see this job ID here. So if I just dump that, oh, I had a typo. Yeah, that's not going to work. Try again. I can just do that. I did something else. Samples here. Oh, is it not going into here? Let's do this. Let's go back here. My cheat sheet. This is the path to the directory where Q sub was run. So I'm just going to make sure that I am in that directory. Okay. There we go. So now you can see, doing linear algebra on a GPU is much faster than on a CPU. Okay, so going back to compilation. Okay, so that's CUDA code. Now we will talk about running with MPI. So I also have an MPI example here. It's the same thing, runs the same thing, just in parallel multiple times. No communication really happening. So again, we're going to compile this again using CC, and we don't have to do anything here. It already knows where the MPI lives on the system. And I mean, I don't want this to be magic, so let's just take a look here. So if I do echo my LD library path, you'll notice, all of these module modules that are loaded are responsible for some of the stuff that's listed here. And so what you'll notice, for instance, there's Cray mpitch loaded here. And that corresponds explicitly to something here in this mess. Where's mpitch? In there somewhere. Oh, maybe not. Maybe CC is really taking care of that. Oops. You can see that there, but where is, maybe on the login or on the login node, you don't see that. So in either case, let's see. Just making sure no questions in Zoom. Okay, so going back to our example. So now let's build the MPI version. Okay. So there we go. Now we've got MPI there. Let me make sure I don't have any silly things here. I'm going to go ahead and add that change directory PBSO workdir. Okay, so this submit script has gotten a little more complicated because we are now using MPI. And so what you'll see is, I need to know the total number of nodes that I'm running on. Now, I don't think I'll be able to submit this to the training queue. I'm going to try just to see. I think we're limited to single node jobs on this queue, which will be a little annoying for this example. But anyway, you can feel free to run this with the debug queue. Let's see, I am down in the examples looking at 0.1 example MPI. So what this is doing here is it's just doing a line count on this PBS node file environment variable. This is a file that lives in /temp, and it literally lists one line at a time every node that your job has been assigned. And so it's really just counting all the nodes that you've been assigned in your job and assigning that to this variable. And then you can define, and of course you can oversubscribe NVIDIA GPUs, right? You can use their, blanking on the acronym, but anyway, you can run more than one process per GPU if you like. But typically people run one process per GPU. And so here I've set the number of ranks per node to the number of GPUs. And now the total number of ranks are the multiplicative of those two values. So when I run MPI exec, I'm going to pass the total number of ranks for all the nodes, and then the number of ranks per node and the executable. Okay, so that's what's changed here. I need to update my queue. And if this doesn't work, we'll try submitting to the queue sub example 0.1 mpi.sh. Yep, that violates the queue limits. So I'm just going to adjust this and make it submit to the debug queue. I can always override the parameters in my script on the command line, which is really helpful for quick changes. So now that job is there. Okay, it's queued there. I don't know how busy the debug queue is, so I might sit there for a few minutes. But for you wanting to run right now, I would just update this to a 1 from the 2. okay? And submit it, and that way you can. Oh, it's already done. Good. So it's not actually so bad. So I'm going to look at the output. There you go. So you can see I had a total of 8 MPI processes, each of them numbered correctly, and each of them printed the runtime. Oh, I do want to explain this. QSMe is not an actual command. That is an alias that I set up that is just defined like this. You can add that to your bash RC if you like. Here, I'll put it in the Google Doc in case people are interested. I think my qstat command is also an alias now that I think about it, because I like a little more information. So that's there as well if you like. Okay, so does that finish compilation? I think it does. So now we'll move on to profiling. And Jae-Yuk is going to take over there.
Okay, so let me, can you hear me?
Yes, let me stop sharing. There we go.
Okay, let me share my screen. Okay, can you see my screen?
Yes.
Okay, so, let me speed up. So Yasi said we don't have enough time. Okay, so I'm gonna quickly touch the profiling part. So in the GitHub repository Taylor showed, you can click the 02 profile.md, and it has a very simple example and a simple case how to run the Nsight system and Nsight Compute. So as you probably know, NVIDIA provide several tools for profiling your application on NVIDIA GPUs. And one of the popular tools on HPC side is NVIDIA Nsight System for profiling GPU and CPU together with the low overhead. So if you have some application at scale, you can try to run with the Nsight System. And then after running there, you will probably find out some important corners or some outliers in terms of performance, and you may want to look into more details for the specific corners. In that case, you can use Nsight Compute tool to get the more detail. So as you can expect, since it provides more detailed data, its overhead is much higher than Nsight System. So if you want to run application at scale, you had better choose the most important corner for the profiling. Okay, so here, as Taylor showed, you can start your interactive job mode for this example. So in this case, we just use debug, but as Taylor put on the this Google spreadsheet here, right? So you can use this queue name for now for training, and then you can use training_Polaris for the project folder. And then I also put some the command lines for this example for profiling. So let me try to show you here. Okay, so I already downloaded ALCF. Sorry, I downloaded the ALCF. I cloned the ALCF beginners guide here. If you go to Polaris here, and then if you go to example, you will see the Babel stream, but it's empty, right? So what you need to do is here, you need to initiate the Git, the sub module from the Git. So Git, sorry. So let's see, Git sub module initiate, and then you need to update Git sub module using the Git sub module update. And then if you go to Babel stream, you can see is cloned the Babel stream. Babel stream is one of the simple benchmark to measure your memory bandwidth, written by the developer at the University of Bristol, and they have a multiple backend. So we will use the CUDA backend for this example, right? Okay, now you have a Babel stream. So in order to make the Babel stream, you can just load proper modules. So for profiling, we recommend to use the CUDA standalone module. So in this example, we used 11.8. And when I checked the module this morning, I saw we also have 12.0 version. So you can try either of them. So in this example, I tried 11.8. It's kind of proven, so you can try it out, right? So if I load module, I load the CUDA Toolkit standalone version and the CMake module to build this Babel stream. In order to build the CMake, the Babel stream, you can just copy and paste this one. So using the CMake, this is easy to use, right? And then it will link the corresponding compiler, and then you can build it with the CMake build Polaris here, right? So let me build it. Okay, now we just configure and build this example Babel stream. So you can go to build Polaris, and then you can see here the CUDA stream, right? So just to let's try to run it, right? So if you just to the CUDA stream, it will run some simple kernels for copy, multiplication, add, and try and dot. And then based on this kernel, it try to measure the bandwidth, right? So as we know, the HBM bandwidth on the A100 GPU is around 1.3 or 4 terabyte per second, right? So as you can see here, with each kernel, we can see some similar performance from the HBM, the memory, right? Okay, and then using this CUDA stream, we will try to run the Nsight system. So this is one of the simple examples: NSys profile -o NSys Babel stream, and then step through and CUDA stream. If you run it here, yeah, I can see a lot of people are copying and pasting. That's good. So if I copy in here, okay, it's running. So standard output is very similar, right? Here, this is the standalone version, and this is with NSys, right? And as you can see here, the bandwidth reduced a little bit, but you can say this is almost negligible, right? From this data, we can say Nsight system is a very lightweight tool. And then it also provides some additional information here. So this is CUDA API, so CUDA malloc and CUDA device, and then this is a GPU kernel data. So as I mentioned here, this benchmark has add kernel, tried kernel, dot, and more than copy kernel, right? And it provides the corresponding data. And then finally generate this NSys Babel stream.nsys.rep and SQLite, right? So there is a two way to post-process this result. One way is using the compute CLI. So if you go to here, if you use NSys and the stat and this in this NSys.rep, you can get the text-based data. But our recommendation is use the GUI interface. So if you go to this link, NVIDIA System, NVIDIA Compute, you can go to the NVIDIA site, and then you can download NVIDIA System and NVIDIA Compute on your local system. So you just need to create the free account on NVIDIA, and then you can get the data. You can get the client version, right? The only thing you need to remember is when you collected the data, your client version should be the same version or newer than the NVIDIA tools used on the Polaris. So in this example, we use the CUDA Toolkit 11.8, right? So, and I think current latest version from NVIDIA is 12.2. So if you download the latest version from NVIDIA Nsight, you can, you're fine to post-process the data collected from the Polaris, right? So to save our time, I don't download and install them, but you can download and install them, and I will just use my local client here, okay? So, and I also already downloaded this the NSys REP file on my local system. So let me just open it up, okay? So this is if you start NVIDIA system on your case, you can see this window, and then you can open. And I already downloaded it, right? So I can just open it up. So if you open it up, you can do CPU and GPU the data, and you can also see the kernel here, right? So there are a lot. This is time series. So x-axis is time, and then we can see some different components. So we can zoom in some portion of the collected data here. Zoom in to selection, and then you can see here. If you zoom in a little bit more, you can see we have add kernel, triad kernel, and dot, copy, and multiplication kernel, and it is repeated, right? And then in order to see the more detailed data, you can see click here, and then if you click the right button, you can see showing event view. So if you click event view, you can see all the invocation of the kernels here. So copy, mul, add, triad, dot, and copy, mul, triad, dot, right? And then you can check also start time, duration, and GPU and the stream case, right? So if you click the one of them here, copy, for example, dot, triad, on the description, you can see a little bit more data here. So what is the begin and end, and then what is grid size, block size, etc. So you can check in this data, right? So this is from this case, you can see the overall the data from CPU and GPU, both of them, right? And then let's move on to Nsight Compute case. So as you can see here, for Nsight Compute, you can just use NCU dash set detail and dash K. So in this example, in previous example, I told you we have the 5 kernels, and then let's assume we are interested in the triad kernel and add kernel. So using the RGX, I added triad and add, and then I tried to generate the data in this NC triad add Babel stream alpha file, right? So if I run it here, you can see this is add kernel, triad is repeated here, right? And then it says 18 passes here, right? So as I mentioned before, Nsight Compute tried to collect detailed data. It tried to replay your kernel several times. In this case, it replayed your kernel 18 times. Because of that, the overhead for this kernel is very high, right? So it's kind of repeating now, and then it will end soon. So once it is ended, you can see the standard output from the application. So previously, all the kernel reported around 1.3 terabyte per second for every kernel. But in this example, we are collecting detailed data for triad kernel and add kernels, and you will see the triad and add kernels performance will be much lower because of this tools overhead, right? So once it is computed, I think it will be done in a second. Once it is done, we can download NCU-REP file here. Okay, here. So standard output here, you can see the copy and mul and dot still shows pretty good bandwidth, but the add and triad is much lower bandwidth and much higher average time, right? The reason is it is replayed 18 times, and then stop and play and stop and replay takes a lot of overhead as well. Because of that, it has very high overhead. So at scale level, you had better avoid collecting all the kernels with the NCU because of the I overhead, right? Anyway, at the end of the collection, you can see this the .ncu.rdp file, and then you can also download it your local client, local machine. And then you can open your Nsight Compute client version here, right? So I already installed on my machine, and then you can open it. Open file here. And I downloaded NCU triad and that file, NCU file. And then if you open it, you can see the summary file. And then you can see now you can only see the add and triad because you collected those specific kernels, right? You cannot see the dot or mul or the copy kernels, right? And you can also see all the invocation of this triad and add kernel here. And then for more details, you can go to detail tab here, and you can choose. In this case, we have add kernel at the very first invocation. So you may choose triad at fifth invocation. And here, GPU speed of write throughput. If you open it up, you can see more detail here. So as you can expect, this is a stream benchmark for measuring the memory bandwidth. So this is a highly memory bound kernel. So you can see GPU throughput is highly memory bound. And you can also see the more information here. And if you go down here, you can see roofline as well, right? So x-axis is the arithmetic intensity, y-axis is clock rate, and then inclined loop represent the memory bandwidth, and the plateau loop represent the compute peak. So obviously it shows the memory bound kernel, right? And then if you go down here, you can see more compute workload analysis, what kind of the instruction have used in this kernel, right? And then memory workload, and the schedule statistics, and WAF state, and other instruction statistics, right? And in some case, you also want to see what is the the assembly for specific kernel, in that case, you can go to source line here. And if you go to source for the triad kernel, you can see what kind of instruction has been executed and then how much cycles has been used, right? For in this case, this is triad kernel, so double precision FMA instruction is main instruction. So you can see 94% of the cycles used just for this FMA instruction, which makes sense, right? So yeah, so I think this is a kind of quick intro of the Nsight system and Nsight Compute, and you can see in this MD file, you can see all the detailed process. So yeah, please try it out and let me know if you have any questions through the chat. Taylor, do you wanna take it over for the next part?
Sounds good. Let's see. The next part should be pretty quick. It's all focused on our Python environments. So, it's not a tutorial on Conda or Python. It's just how to load modules, how to build custom environments. And I think you've already seen this play out on my command line. You see we use this module load Conda. There's a default Conda specified if you don't specify the date, as I mentioned before. So if I go to module avail Conda, you'll see our Conda environments available. This one is the default. So if you just say Conda, this is the one you'll get. These are the pre-built modules that go in there, the ones that we're really focused on having, capable of running and need to be custom built for our system. There are a lot of other things included, obviously, especially things that support, dependencies of these modules, but those things didn't require custom builds. That's why they're not listed. So you can use these. So for instance, if I if I do the default, so module load Conda, and then if I do Conda activate, okay, so now I've got the Python that comes with this. I can do Conda list. This will tell me all the Conda packages that are installed eventually. Okay, so you can see things like Torch, TensorBoard, TensorFlow. What are some other things people would, there's NumPy, of course. Hopefully, yep, Matplotlib is in there. We've got some Jupyter support stuff, right? So there's a lot of packages installed here. You can always take a look. You can also do pip. Can you inspect? Well, pip has an avail or not. But usually the pip installed modules will be showed here as well. You can use either. So you can do things like pip install -- user and then the package name, right? And what this is going to do is it's going to install additional packages in my .local lib Python, and you can see I've used this before down in site packages. Right, so I've used this for image data set loader, right? So if you have some small dependencies that you want to install in addition, you can just do that. Just do pip install user. It'll put it down in your home directory down in these places. If you really need big changes where you're going to be custom build, even with custom builds, you could do it this way. But anyway, if you really desperately want a sub environment, we have instructions for doing that. So you can use virtualenv. The trick here is that you need to include this system site packages. We have libraries, right? So if you do which conda, this is where the base directory for conda. We have things in /lib for MPI and CUDA and such to make all of those things work properly. If you skip this, you're not going to bring all of those things with you into your environment. So you'll want to include that if you're using virtualenv. The other option is cloning the conda environment, and you do it with this command here, where you create a clone of the base environment. And then you can activate your clone. You tell it where to install the clone, right? So you can create those, and then with these two situations, so with this one, you're using pip, right? So you do pip install, and it's going to install it into your new place. Here you can do conda installations, you can do pip installations, and again, it's all those files are gonna be in this path that you've specified. I'm not gonna go through each of those. I think it's pretty straightforward process here. Feel free to work through those examples during this tutorial. I see this question from Alfred. Alfred, keep in mind that this is all on the file system, and it's a shared file system. So of course it's going to be on all the nodes. Okay, and we also have a specific documentation for Polaris with using Python. So there's more details here, but a lot of it was replicated in this text here. So the next step is Jupyter. If you're interested in using Jupyter, we have a Jupyter server. I would say I have not personally used this a lot for large scale workflows, right? If I'm running a lot of multi-node jobs, I tend to just use Python scripts. Because if you want a lot of nodes, you're going to sit here in the web UI waiting for your job to start. But in our example, or in this tutorial, that is, we have a reservation, so it should be quick. So we have a separate login for each of our machines. So I'm going to go to login Polaris, and I'm going to type in my ALCF username. I'm going to get out my phone, get the mobile pass out here, type in that password. Okay, so I have to submit a job to the queue if I want GPUs. Otherwise, I'm just sitting on the login node. So I want a Polaris compute node. And since we tend to limit what queues people can submit to. So in this case, you would have to use the debug queue. I'm going to use training Polaris since it's listed, and I'll do one node, and I'll do 15 minutes. And I have to tell it which file systems I want. I'll just stick with home for the moment. So I'll click start. And what that's going to do, it's going to put my job in the queue. So, if I go back here, I can see it sitting there. Looks like it's already started running. That's good. So you can see the page is reloaded, and now it's launching my job here. I can specify which kernel I want to use. And when you come up by default, it's Python 3. And I think what you guys will actually see is something more along this when you first come up. I don't know, maybe it gives you the immediately dumps you into the untitled one. I don't know. I don't know if that's just because that's where I left it when the last time I used it, or but anyway, there's the launcher. If I hit this plus, Python 3 is the system Python 3 slash user bin Python 3 or user or slash bin Python 3. I don't know which. It does not have anything useful in it, unfortunately. So you have to add one of these CUDA environments to your notebook. And so we have instructions for that right here. And so what you're going to do on the command line, and since I've already module loaded and activated Conda, the next thing I'm going to do is I'm going to run this Python command, because I mean, when I run Python, it's giving the one from Conda. And what this command does, and I have to specify some things here. The display name is the thing that gets listed here, okay? So that I know which one I'm using. Kernel, or the name itself, I think has to do with the file name that's written. Yeah, here you go. So this installs kernel name in this path, but actually this ends up in your home directory. Did I list that somewhere? We'll try and find that quick. But anyway, so the kernel display name is the thing that you want to change to something useful in here. So in my case, I set it to data science / Conda, but you can set it to whatever you like. So I'm going to go in here. Let's see if I can copy and paste this. Okay, so Python 3, use that. User just specifies it's going into my home directory. And I'm going to use name is Conda / and then I'm going to use the date from my Conda environment. And actually, I think this should probably be a dash, since this is going to result in a file name created. Whereas the display name, I will just use Conda / I'll just leave that the same too, it doesn't matter. Okay, and then we're just going to use the default paths and LD library path. We want to make sure MPI is enabled and tell it where to find Conda. Okay, so if I run that, oh good, it told me where it put it. Okay, so that makes it easier. So you can see where it places that configuration file. Now, the next time I start up Jupyter, I hope, so this will help show something else. When we when we log out, we'll do shut down all kernels. I'm just going to do a quick Q stat here. My job is still running. All the kernels are stopped. Oh, if I go to hub control panel, that's what I was looking for. I can do stop my server. This does not exit my job. So I still have this node. Only when I log out, I believe, is when it kills the job that's in the queue. But now I can restart my server. Oh no, maybe it didn't. Oh yeah, it did. It exited. Okay. So I'm going to resubmit real quick. Debug. 15 minutes. start that. If you do navigate away from the web page without shutting down your server, your job will sit there in the queue and chew up your allocation. So you do need to make sure you shut down your server at the end of the job. Or you can come down here and do a QDel. That also works. Okay, so my job's in the queue. I assume everybody here is probably trying to get on, which is fine. But the point is, when I come back and I list the kernels, I should be able to now see that Conda environment available. And the reason we do this is so that if you end up cloning environments or creating your own environment, you know how to add this to your Python Jupyter instance so that you can always load that up as the running kernel. And that's pretty much it for Jupyter. There is this thing with this note about accessing project files. When your Jupyter notebook starts, you can only see your home directory. So if you want to navigate to a project directory, just add a symlink to the project directory in your home directory, and that'll allow you to go there. Okay.